is Dr. Sridhar, back to you with another video session on some of the numerical problems associated with the single phase transformers, and with the help of these numerical problems we can get more knowledge and perfection on phasor diagrams of single phase transformer. Let us start with the basic problems in single phase transformer. So first problem is a single phase transformer has 480 turns on the primary winding. So primary winding, let us draw the simple structure of the transformer. So here this is nothing but the primary winding, these are nothing but the secondary windings. So turns they have mentioned here. So primary windings are nothing but the N1 is equal to 90 and N2 will becomes, sorry, N1 is equal to 480, N2 is nothing but the 90. And the maximum value of the magnetic flux density is nothing but the maximum value of the magnetic flux density. So is equal to 1.1 Tesla when 2200 volts and 50 Hz is applied. So V1 they have given that is 2200 volts and 50 Hz is nothing but the frequency of the winding. Calculate the maximum flux in the core. So let us go back to the formula, that is induced EMF of single phase transformer is nothing but 4.44 into pi max into F into N. This is nothing but for N1. If you are taking the primary value, then this will becomes N1. Otherwise, secondary induced EMF means it becomes N2. So this value is 4.44. This is pi max. So pi max is not available. So pi max is nothing but B max. So actually the formula for B max is nothing but, so maximum flux density B max is nothing but that is pi max to area. So maximum flux to the area. So if you could calculate, pi max is nothing but B max into A. So this is the formula we are going to use. The next one is maximum flux in the core. So maximum flux in the core, how it can be calculated. So here EMF of the primary, that is nothing but 2200 they have given. So on the left side if you could write 2200 is equal to 4.44 into pi max into F is nothing but 50 Hz he has given into 50 Hz into primary turns also they have mentioned. So that is 480 number of turns. If you are simplifying this particular expression, you will get straight away pi max, which is nothing but 20.6 milliwebers. So this is about the first bit. Second bit is the cross-sectional area. Let us use this formula to find out the cross-sectional area. Here, this B max they have given 1.1 Tesla and pi max also we have computed, that is 20.6 milliwebers, and A is equal to pi maximum by B maximum. So we can easily get 0.0187 meter square. So this is nothing but the cross-sectional area. And last one is the secondary induced EMF. So what is this secondary induced? See, it is secondary induced EMF. So that is nothing but how much of E2. So for a while you can assume E2 is equal to V2. So we know the transformation ratio. So that is nothing but transformation ratio is equal to K is equal to V2 by V1 is equal to N2 by N1 is also equal to E2 by E1. So here V2 by V1, V2 we don't know, but V1 we know, that is 2200 is equal to N2 is also available for us, that is 480 divided by 90. So if you are simplifying this, you can easily find out V2, which is also equal to the E2 value, that is nothing but the 412 volts. So this is a basic problem, and with the help of transformation ratio, how we are going to calculate the voltage by knowing the voltage in one winding, and how it will be, that is nothing but the transformation ratio, it will be useful to know the other circuit parameters in the single phase transformer, and how this cross-sectional area it can be computed, and maximum flux density, maximum flux also. This will be how this EMF equation it will be useful to know some of the associated parameters of the single phase transformer. Let us take one more problem for better understanding of the phasor diagrams. That is A single phase transformer has an energy component IA is equal to 2 amps and a magnetizing component of 2 amps and a magnetizing component IM of 5 amps. So here, so magnetizing component IM or sometimes I mu is also used to represent this. So this is the 5 amps and calculate the no load current. I naught is how much and working component or IC is nothing but they have given 2 amps. This is nothing but energy component and I naught and resulting power factor. So how can we compute this I naught? So what is this I naught value? So I naught is nothing but square root of IW square plus I mu square. So this is the formula used. So 5 square plus 2 square. So we are going to get the 5.4 amps. So how we are going to get this value means, now from the phasor diagrams if you could see, this is the flux and this is I naught. Now if you could take this as the V1 supply voltage, so you can resolve this component into two perpendicular vectors. So this is nothing but I mu or IM magnetizing component. So this component is nothing but IW or IC. So this value is nothing but the pi naught. So in this one, let us take this I mu or Im is nothing but this value is equal to I naught into sine pi naught. So this value is equal to 5 amps. Or otherwise, you can make use of this formula also. IW is equal to IC is equal to I naught into cos pi naught, which is nothing but this is the 2 amps. So from this expression, now we know I naught. So that is IW is equal to 2 amps is equal to I naught is equal to 5.4 into cos pi naught. So if you are simplifying this equation, so no load power factor is equal to 2 by 5.4. So this is a method to calculate no load power factor and this is a method to calculate the no load current. So these we can, in this analysis, we have utilized the phasor diagrams of single phase transformer under no load conditions. So in the same manner, let us take one more problem. That is, a single phase transformer has 1000 tons on its primary winding. So primary winding has 1000 tons and 200 tons on its secondary winding. The transformer is a no load current taken from the supply is 3 amps at a power factor of 0.2 lagging. Just now also we have discussed about the phasor diagrams. So I naught they have given that is the 3 amps and no load power factor is nothing but the 0.2 lagging. So calculate the primary winding current IP and its corresponding power factor when the secondary current supplying a transformer loading is 280 amps at 0.8 lagging. So this is a very important problem because here just now in the previous case we have studied the transformer under no load condition. Here in this current problem we are going to discuss the transformer under loading condition. Now it is very clear before starting to this problem. Now let us recall the fundamentals what we have studied in our previous videos, that whenever a load is applied on the secondary, proportional to that particular load, primary winding will draw some amount of excess amount of current from the source, which is corresponding to the load current I2. That available current in the primary is I2 dash. So finally in the primary winding, there will be two types of current. One is a no load current I naught and next current is nothing but the load equivalent in the primary. So that is nothing but the I2 dash. So total primary current I1 is nothing but the vector sum of no load current I naught and load equivalent, that is nothing but the I2 dash. So if you could know these things, we can easily solve this problem. And of course, there are so many power factors are there. Don't confuse with this. Of course, it is very simple. Only the thing we have to remember that is that primary current is nothing but the vector sum of no load current I naught and load equivalent, that is I2 dash. That thing is very important in this problem. So already we know that primary to the secondary, that is NP is primary to NS is nothing but the secondary, is equal to IP to IS, that is the primary. Of course, primary are subscript with 1 or secondary is subscript to with 2 also we can make use. And primary current is nothing but, now by using this transformation ratio as K, we can also calculate NS into IS divided by NP, 200 into 280 by 1000. So straight away you can get the primary current, that is 56 amps. So primary power factor also we can compute, that is 45.444 divided by 58.3. So that is nothing but 0.78, that is 38.3 degrees. That is the no load power factor. So you can also calculate various power angles corresponding to the point 2. That what is that point 2? That is the no load power factor. This is the primary power factor, and this point 8 is corresponding to the pi 2 dash. Let us clearly write pi 2 dash is nothing but 36.8 degrees. So this is the power factor of the load component in the primary winding. So pi 2 dash, because they have given that supplying a transformer loading is 280 amps at 0.8 lagging. Of course, this is pi 2 dash. Anyhow, this will be same because it is going to extend in the reverse direction. So load power factor is 36.8 degrees. So IX component, because you can also recollect the basics like this is flux pi, and sorry, this is E1 vector and this is the E2 vector. And if this is the voltage V and this might be the current I2, if you are extending this current in the opposite direction, this would becomes I2 dash. And if you could say this is the I0, then if you could construct, and this diagonal will be the I1 current. So how much of angle it is going to take with this, that is nothing but the pi 1. This is the angle how much it is going to make it with is pi naught. And this is corresponding to angle this, and this angle is nothing but the I2 dash. Anyhow, we know that. So IX component is nothing but if you are revolving this, or you can directly straight away you can go with the phasor diagram and you can compute this. IX component is nothing but, now this is the one component, and I1 component also we are projecting onto the reference axis. Then 3 into sine 78.5. This is anyhow that angle we have calculated, and this is the sine 36.8. This is the secondary loading phase angle. So 56 star sine of 36.8. So we are going to get Ix is equal to 36.48. Similarly, Iy is also 36.48. Sorry, this is 45.44 amps. So this is 45.44. And finally, the primary current is nothing but the square root of Ix square plus Iy square. So this is, if we are extending this square root up to this, so primary is nothing but 58.3 amps. So like this, we can also compute our straight away by taking this trapezoidal rule. Also, you can easily compute. Of course, I think phasor diagram will also helpful, and it provides multiple ways to solve the problem. So, and one more last problem in the transformer is, it is talking about the efficiency calculation. A 400 kVA transformer has a primary winding resistance of 0.5 ohm and a secondary winding resistance of 0.001 ohm. The iron loss is 2.5 kilowatt, and the primary and the secondary voltages are 5 kV and 320 volts respectively. If the power factor of the load is 0.85, determine the efficiency of the transformer on full load and on off load. So this is the problem here. It is full load means it is 100% load. Off load means X is equal to 0.5 only, because 50% of the load. So rated output they have given, that is a 400 kVA output clearly mentioned. This is what is the rating of the transformer. So rated output is 400 kVA, that is 400 into 10 cube VA. And next one is full load secondary current is nothing but rated output to the voltage. So 400 into 10 cube divided by the VT. At what voltage they have clearly given, that is secondary, primary and secondary voltages are nothing but 5 kV and 320. So if you could substitute that values, so straight away we are going to get the rated secondary current is 1250 amps. So total resistance refer to the secondary. Let us shift the total resistance into the secondary winding. R2 anyhow it will remain same. Only R1 it is going to change. R1 into K square. R1 into K square is the formula. What is the K? K is nothing but the transformation ratio, that is V2 to V1 or N2 to N1, with which you are convenient you can take that value and just to substitute here. Now the total resistance referred to the secondary is 0.033 ohm on full load copper loss, because here that copper loss is also very, very important. So full load copper loss is equal to I2 square into R02 or RES. So 51.5625 kilowatt. If you are substituting this I2 current 1250 whole square and this resistance, now we are going to see 51.5625 kilowatt. So what is the iron loss? Iron loss is, they have clearly given the iron loss is equal to 2.5 kilowatts. So 2.5 into 10 cube watts. So these are the losses the transformer is having under full load conditions. So transformer efficiency at full load and 0.8 power factor is equal to, let us recollect the formulas from our previous videos. That is, efficiency is equal to x into V2 I2 cos pi 2 divided by x into V2 into I2 cos pi 2 plus Pi plus Pc. So if you are substituting all the values, x is equal for full load, it is 1 only. So remaining values, if you could substitute, this is 86.2 percentage. Similarly, transformer efficiency at off load means x is equal to 1 by 2. Just now also we have discussed, that is nothing but the 0.5. If you are substituting here, that is 91.69 percentage. You see, under full load condition, the efficiency is 86.2 percentage. At the off load condition, that is 91.69 percentage. Now, these are the few problems we identified for better understanding of the phasor diagrams and formulas what we discussed in our previous videos. I hope you enjoyed this video session by solving different problems. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.